Scientists estimate 2 trillion galaxies stretch across distances light, takes billions of years to cross. And in all of that immensity, across all of that time, across all of those stars and all of those worlds, we hear nothing, no signal, no reply, no one. We have been listening for over 60 years. We aimed our best instruments at the sky and waited with extraordinary patience and increasingly sophisticated technology. What came back was silence so complete, it defies every reasonable expectation the mathematics of the universe should produce. There is a number that should not exist. It is the number of confirmed alien civilizations humanity has ever contacted. That number is 0, not close to 0, not approximately 0, exactly 0. Think carefully about what that means before moving forward. Our galaxy alone holds somewhere between 200 billion and 400 billion stars. Scientists now confirm that most stars have planets orbiting them. Many of those planets sit inside what researchers call the habitable zone, that narrow band where liquid water can rest on a surface without boiling away or freezing solid. Estimates place tens of billions of Earth-sized worlds in our galaxy alone. And yet the count of confirmed contacts remains exactly 0. For more than 60 years, we have been broadcasting radio signals into space. Those signals have already swept outward hundreds of light years in every direction, passing through thousands of star systems, washing over untold numbers of worlds. We have also listened using massive dish antennas, scanning the sky for any pattern that nature alone could not produce. The silence we received in return has a name. Physicists call it the Fermi paradox, named after physicist Enrico Fermi, who in 1950 asked a question so plain it almost sounds careless. He said, "Where is everybody?" He was eating lunch with colleagues, talking casually about the probability of alien life, and the question just fell out of him. Where is everybody? It turns out that question is one of the most dangerous things a mind can ask, because the math does not hold together. If even a small fraction of those tens of billions of Earth-like worlds developed intelligent life, and if even a fraction of those civilizations reached a point of launching self-replicating probes capable of spreading across the galaxy, then the entire Milky Way could have been explored within just a few million years. A few million years sounds immense, but our galaxy is over 13 billion years old. On that scale, a few million years is shorter than a single afternoon. In 13 billion years, no visitor has arrived, no message has been decoded, no beacon has ever been confirmed. That silence is terrifying because every explanation we reach for turns out to be worse than the one before. Maybe life is far rarer than we assumed. Maybe something stops civilizations before they can spread. Maybe something out there is listening but has chosen to say nothing. Maybe we are too young, too primitive, too quiet to have been noticed. Or maybe the universe is empty for a reason. And the deeper you look into that reason, the more unsettling each layer becomes. The next explanation on the list is not comforting. It is the kind of calculation that makes researchers pause before they say it out loud. What if the silence is not an absence at all? What if it is an answer? The numbers are the problem. Once you see them clearly, the silence stops feeling like a mystery and starts feeling like a verdict. Our galaxy contains between 200 billion and 400 billion stars. The Kepler Space Telescope confirmed that nearly every star hosts at least one planet. Roughly 1 in 5 stars similar to our own sits at the right distance for liquid water to exist on a rocky surface. That alone gives us somewhere around 40 billion potentially habitable worlds inside the Milky Way. Apply even the most cautious version of the Drake equation, the formula astronomers use to estimate communicating civilizations in the galaxy, and the numbers refuse to cooperate with the silence. If only 1 in a million of those habitable worlds produced life, and only 1 in a million of those developed intelligence, you would still expect civilizations to exist nearby. In cosmic terms, we find zero. The paradox goes deeper than just the absence of a signal. Physicist Michael Hart calculated in 1975 that a civilization expanding at even 1% of the speed of light could colonize every corner of the Milky Way in roughly 5 million years. Do it slower, and the math still works long before the universe reaches its current age. So why has no one come here? Why are there no ancient structures on the far side of our moon? Why did no passing fleet stop by 10,000 years ago and leave a marker? The universe has had billions of years. The math says someone should have arrived. The fact that they have not means one of a few things. Either civilizations are almost impossibly rare, or something prevents them from spreading, or they came and made a deliberate choice about us. Physicist Stephen Webb catalogued over 50 proposed solutions to the Fermi paradox in his research. Some are consoling, most are not. What they share is this: no matter which explanation you choose, the universe ends up looking like a place where intelligence is fragile, scarce, or actively held back. There is a third possibility Webb mentions that some researchers find the most disturbing. What if civilizations do reach the stars, and when they find a younger world with radio signals, they make a deliberate choice to say nothing? What if silence is not indifference but policy? That idea connects directly to something in game theory, in economics, in the cold logic of survival across vast distances. That makes it harder to dismiss than it first appears. Most people have no real sense of how empty space actually is. Not in an abstract way, in a physical, measurable, almost suffocating way. The universe is mostly nothing. Here is one way to feel it. If our solar system were compressed to the width of the United States, our nearest neighboring star system would be sitting somewhere across the Atlantic Ocean in Europe. And that is the closest neighbor we have. Everything beyond that stretches further still. Our galaxy is a disk roughly 100,000 light years across. Traveling from one edge to the other at the absolute speed limit the universe allows would take 100,000 years. At the pace of our fastest existing spacecraft, it would take something close to 2 billion years. The Milky Way is one of an estimated 2 trillion galaxies in the observable universe. Between galaxies, the emptiness becomes something different entirely. The gap between our galaxy and the next large one, a giant called Andromeda, spans about 2.5 million light years. Inside that gap, there is almost nothing, a few lonely hydrogen atoms per cubic yard, temperatures hovering near absolute zero, no stars, no planets, just a cold, enormous void. This is what the universe actually looks like up close. Clusters of matter separated by distances so vast that even light struggles to seem fast. Even if a civilization in a distant galaxy developed the ability to send a signal in our direction, that signal would travel for millions of years before arriving. The civilization that sent it could have risen, flourished, and vanished long before the first photon from their transmitter reached our telescopes. Distance and time are both working against contact. Two civilizations could coexist, and never know about each other simply because the gap between them is physically too large to bridge within the lifetime of either one. There is also the cosmic horizon to consider. The universe itself is expanding. Space between us and distant galaxies is stretching. Carrying some of them away faster than light can close the gap. There are galaxies visible through our most powerful instruments right now that we could never physically reach, even at the speed of light, because the expanding space between us and them will always keep them ahead of anything we send. In the year 2000, two scientists named Peter Ward and Joe Brownlee proposed something that made their colleagues genuinely uncomfortable. Their argument, which became known as the rare earth hypothesis, said that complex life on Earth did not just happen to exist. It existed because of an extraordinary chain of coincidences, each stacked on top of the last across billions of years. Remove any single link, and we are not here, start with location. Earth orbits our star at exactly the right distance to keep water liquid on the surface. Move us closer by 10% and the oceans boil away. Move us further out by 15% and they freeze solid. That stable distance has held for over 4 billion years, giving life the time it needs to develop from the first chemistry into something capable of asking questions about its own existence. But orbital distance is only the beginning. Our solar system sits in a specific band of the galaxy, sometimes called the galactic habitable zone. Too close to the galactic center and the density of stars and radiation events would repeatedly sterilize any planet. Too far out, and the heavy chemical elements needed to build rocky worlds and biology simply are not abundant enough. We sit in a narrow middle ground where the chemistry is rich and the radiation is survivable. Then there is a giant planet sitting further from the central star, acting as a gravitational shield, pulling in or deflecting many of the large rocks and frozen debris that would otherwise hammer the inner planets with catastrophic frequency. Without that guardian, Earth would have been struck far more often, possibly preventing complex life from ever gaining enough stability to grow. There is also the star itself, burning with unusual consistency for its type. Many stars pulse, flicker, or release enormous bursts of radiation that would strip an atmosphere or cook biology repeatedly. Ours has burned steadily for over 4 billion years. And then there is something we rarely think about: plate tectonics. The slow grinding of Earth's crust continuously recycles carbon, regulates temperature, and rebuilds the chemical nutrients that biology depends on. Most rocky planets we know of have no active tectonics. Earth does. The list keeps going. Our planet's size gives us just enough gravity to hold a thick atmosphere, but not so much that movement becomes impossible. Our iron core generates a magnetic field that shields the surface from the worst of stellar radiation. Even the angle at which we tilt is held stable by the gravitational presence of our large moon, in ways that keep our seasons from swinging into lethal extremes. Each factor seems modest on its own, but stacked together they begin to look less like a series of fortunate accidents and more like a lottery that hit the jackpot on every single draw for 4 billion years straight. If Earth is genuinely this rare, then the silence of the universe is not strange at all. It is the expected sound of a cosmos where worlds like ours almost never form. In 1998, an economist named Robin Hanson published a paper with a title that reads like academia and lands like a threat. He called it The Great Filter. The idea is this: Somewhere between lifeless chemistry and a civilization capable of spreading across the stars, there is a step so difficult, so lethal, or so unlikely that almost nothing survives it. Hansen called this step the Great Filter. It is the invisible wall that separates the universe we observe, one full of ingredients for life, but apparently empty of civilizations, from the universe that math predicts, one that should be buzzing with visitors and signals. Something is stopping civilizations from spreading. The Great Filter says that something is one particular barrier, perhaps just one step in the long climb from simple atoms to an intelligence that can cross the void. The question is not really whether the filter exists. The silence makes a strong case that it does. The terrifying part is figuring out where it sits in relation to us right now. Two possibilities, and they are worlds apart. The first is that the filter is already behind us. This means we crossed it. Some step in our past, perhaps the origin of life from raw chemistry, perhaps the leap from single cells to complex multicellular organisms, was nearly impossible. We made it, others did not. The universe is quiet because most worlds could not survive the obstacle we already passed. If that is true, it is actually hopeful news. The worst may be behind us. The second possibility is that the filter lies ahead. This would mean the wall has never been cleared. Every civilization that has ever reached our stage of development eventually ran into something and was destroyed. A war that went too far, a technology that got loose, something we have not yet imagined. And the silence of the cosmos is not emptiness. It is the sound of every civilization that tried and failed before they could leave any mark we would recognize. Hansen's paper points out something crucial. A cosmos with abundant simple life but no complex life would suggest the filter was the step from simple to complex already behind us. A cosmos with complex life on multiple worlds that vanished would suggest the filter sits somewhere between complexity and survival. And one discovery in particular would be the single most terrifying piece of information in human history. If we ever found clear evidence of an intelligent civilization elsewhere, one that existed and then vanished, it would nearly confirm the filter is ahead of us. That finding would look like a triumph. People would celebrate. It would be called the greatest discovery ever made. And it would also mean that something out there destroys everything that reaches our level. Something patient, something consistent, something that has been working for billions of years. There is a thought experiment that divides scientists into two groups. The way you feel about your own answer reveals something uncomfortable about the future of everything we have built. Imagine a probe returns photographs from Mars tomorrow morning. Inside an ancient crater, perfectly preserved in rock that has not moved in billions of years, are fossilized microbes. Definitive, undeniable. Life existed on Mars. Most people would celebrate. It would be the greatest scientific discovery ever made. Proof that life is not a one-time accident limited to Earth. But philosopher Nick Bostrom wrote that this discovery would be, in his exact words, the most terrifying news in human history. He was completely serious. Here is why. If simple life arose on Mars independently from Earth, it means the jump from chemistry to life is not the great filter. Life gets started relatively easily. The filter must therefore sit further along the path, somewhere between simple organisms and the spacefaring civilization capable of crossing the galaxy. And since no such civilization has ever been confirmed across all the billions of years this universe has had to produce one, The filter between simple life and a galactic civilization must be extraordinarily effective. Something between where we are right now and where a truly advanced civilization would be is ending everything that tries to cross it. Finding life on Mars would be beautiful. Finding it would also mean we are probably walking toward the same wall. Now imagine a worse discovery. Complex life on Mars. Remnants of something with nervous systems. Something that processed information and responded to its environment with intention. And it is gone. Every trace of it destroyed from the inside out. That discovery would essentially confirm the filter sits directly ahead of us. Complex intelligence has appeared in our own solar system before, and it ended. What stopped it? What made a world capable of producing complexity fall silent forever? Researchers who study the Fermi paradox tend to land in two very different emotional places. There are those who find comfort in the idea that we are rare survivors, special enough to have crossed the hardest step already. And there are those who read the silence of the universe and hear something else entirely. Aftermath. The quiet after something ended. In 1973, astronomer John Ball proposed an idea so strange it felt impossible when he published it. And the longer you sit with the evidence, the harder it becomes to simply set aside. He called it the zoo hypothesis. The premise is direct. Advanced civilizations exist throughout the galaxy. They know we are here, and they have collectively agreed, for reasons we can only guess at, to leave us alone, to observe, to stay silent, to let us develop without interference. The way a researcher watches an experiment without touching the equipment. Like animals in a zoo watched by something that understands far more than we do and has decided not to make itself known. Before this sounds like wishful thinking, consider what contact looks like from their perspective. Imagine a civilization 500 million years more technologically advanced than we are. That gap is roughly comparable to the difference between us and a sea sponge. We do not beam radio signals at sea sponges. We do not send ambassadors. We observe, document, and avoid disturbing their ecosystem. The logic of non-interference is not an alien idea to us. We practice versions of it already with isolated human communities and with newly discovered species. Applied at galactic scale, the zoo hypothesis says that any signal we send outward would be intercepted and not replied to. Any probe we launch would be quietly monitored. The silence would not be natural. It would be maintained. The most common objection is coordination. Why would countless completely unrelated civilizations all agree to the same policy? But this objection assumes civilizations must agree independently. The more likely scenario, if this theory holds, is that there is a dominant culture, an older, more widespread civilization, whose norms have spread across the galaxy the way a single powerful culture can set the rules of an entire planet. Younger civilizations simply learn the rules on arrival. There is a colder version of this idea that some researchers find even more unsettling. What if we are not in a zoo, but in something closer to a preserve, kept intact not out of respect, but because something else has a stake in what we become? What if we are being cultivated toward a specific outcome, and the silence is part of that process? That question connects directly to a theory that is darker and more mathematically grounded, one that suggests the reason advanced civilizations stay quiet has nothing to do with respect or ethics or curiosity. It has to do with survival. And if that theory is correct, then the silence is not the sound of something protecting us. It is the sound of something afraid, something that knows the rules of a universe far crueler than it first appears. And the worst part is this: we may have already broken those rules. We have been announcing ourselves for over a century. If anyone is listening, they have known where we are for a long time. Chinese author Liu Cixin described a theory about the silence of the universe so precise and so disturbing that once you encounter it, it is nearly impossible to think about the cosmos the same way again. He called it the dark forest. Picture the universe as a vast, lightless forest. Inside that forest, every civilization is a hunter. Every hunter knows other hunters exist. Every hunter understands that any creature it encounters could either be an ally or a predator. And every hunter also knows that the price of guessing wrong, of assuming friendship when the other being intends destruction, is total extinction. In that situation, the logical strategy is never reveal yourself. And if you discover another hunter before they discover you, eliminate them immediately before they grow strong enough to pose a threat. Before this sounds like fiction, consider the game theory behind it. The speed of light means there is no real-time communication across the stars. You send a signal. You wait years for a reply. By the time you receive a response, generations have passed. Intentions can shift. A civilization that seemed peaceful when it transmitted its reply might have changed entirely by the time its words arrive. You cannot verify anything in real time. Trust is impossible to establish across those distances. Worse, technology compounds the problem. A civilization that appears harmless by current capability could develop a weapon capable of crossing light years within a century. By the time you realize they have become dangerous, it is too late to stop whatever they launched years ago. In this model, every rational civilization converges on the same conclusion. Stay silent, stay dark, and remove any civilization that reveals itself before it becomes strong enough to remove you first. If the dark forest is real, then we made a catastrophic error. We have been broadcasting radio waves for over 100 years. Our signals have been expanding outward at the speed of light, announcing our existence, our location, and our technological level to anything capable of detecting them. We placed a diagram pointing to Earth on probes launched in the 1970s and sent them into interstellar space. We transmitted a deliberate message toward a distant star cluster in 1974. We have been doing the equivalent of lighting a fire in the middle of a dark forest and shouting into the trees. Some scientists have begun calling this practice active contact, the deliberate broadcasting of signals into space, and they have organized formal conferences to debate whether it should continue or stop entirely. But if the dark forest is real, stopping now may change very little. Something may have already heard us, and the theory that follows does not require another civilization to be listening at all. It requires something older, something automated, something that was built and set loose long ago, still running, still searching, still doing exactly what it was designed to do. There is a simpler explanation for the silence, one that requires no alien hunters, no managed perimeters, no ancient machines, one that is in many ways the most frightening answer of all, because it requires no outside force whatsoever. What if civilizations almost always destroy themselves? The timeline on Earth is worth examining closely. In roughly 150 years, humanity went from steam engines to nuclear weapons, from telegraphs to artificial intelligence, from horses to spacecraft escaping our solar system. The acceleration of our technological capability has been extraordinary by any historical measure, and almost every major leap has introduced new ways to cause catastrophic harm. Nuclear weapons arrived before international frameworks to control them were mature. Biological engineering is advancing faster than biosafety regulations can track. Artificial intelligence is growing more capable faster than our understanding of how to align it with human survival. Each of these represents what researchers call an extinction-level risk. A technology so powerful that its misuse or accidental failure could cause collapse on a civilizational scale. Now consider that every civilization that ever developed technology faced the same arc: fire, weapons, industrial chemistry, nuclear physics, biology as an engineering tool. Each step brought capability and risk in equal proportion. The great filter might simply be the moment when a civilization's destructive power grows faster than its wisdom. The troubling aspect of this theory is that it does not require malice. It does not require a war voted on and decided, a laboratory accident with an engineered pathogen, a miscalculation inside an automated weapons system, an artificial intelligence pursuing an objective that seemed harmless on paper and turned out to be catastrophically wrong in practice. These are active concerns among researchers right now, not hypotheticals from science fiction. Astronomer Carl Sagan wrote extensively about what he called the problem of cosmic adolescence. Every civilization eventually reaches a stage where it holds the destructive power of a god and the wisdom of a child. The only question is whether it can survive long enough to grow up. Sagan was hopeful. Many researchers who came after him are considerably less so. When you combine the statistical silence of the universe with the observed pattern of exponential technological growth on Earth, one conclusion becomes very hard to argue away. If self-destruction is even a common outcome, not a universal one, just common, then the emptiness we observe is exactly what we would expect to find looking outward. Quiet galaxies would be the natural output of a universe where intelligence tends to ignite its own ending before it learns to manage what it built. And yet, even this cold picture is not the strangest explanation being seriously discussed. There is a theory so disorienting it calls into question whether the universe we are measuring is real at all. And the strangest part is that it cannot be proven wrong. Philosopher Nick Bostrom published a paper in 2003 that proposed 3 possible realities. Only one of them is remotely comfortable. The paper is called "Are You Living in a Computer Simulation?" The logic works like this. If civilizations generally survive long enough to develop sufficient computing power, they will eventually be capable of running detailed simulations of minds and of entire realities. These simulations would be functionally indistinguishable from the inside. You could not tell the difference between existing in an original universe and existing in a model of one. If that happens even once, if any civilization ever builds this kind of technology, they will almost certainly build many of these simulations, perhaps billions of them. Each simulated universe could contain simulated civilizations running their own simulations in turn. Very quickly, the number of simulated realities would tower over the number of original ones by an astronomical margin. If simulation is possible at all, the odds that any given observer is in the base layer original universe become vanishingly small. Now apply this to the silence. If we are inside a simulation, the emptiness of the cosmos has a completely different explanation. The universe does not need to actually contain alien civilizations. It only needs to appear consistent and rule-following to the observer inside it, like a video game that renders only what the player can see. A simulated universe might leave most of its volume as an untailed backdrop. Consistent physics, consistent light, no actual content behind the horizon we can never reach. The silence would be a feature of the model. It would be designed in. The truly unsettling aspect is this: the simulation hypothesis cannot be falsified. There is no experiment you could run, no measurement you could take that would definitively confirm you are in an original reality. Any result you gathered would be part of the system generating your experience. If the universe is a model, the silence is a design choice. Philosopher Stephen Baxter proposed one of the most disorienting ideas ever attached to the Fermi paradox. He called it the planetarium hypothesis. Once you hear it, it stays with you. The idea is this: the universe we observe may be a constructed environment, a false sky placed around our world by a civilization so advanced that the distinction between a real cosmos and a perfect imitation of one no longer applies. Not a simulation in the computational sense, something more specific, a physical manipulation of what reaches us. An entity or system that intercepts the light and signals traveling toward Earth and replaces them with a curated version of the universe. One that appears empty, one that appears consistent with our laws of physics, one that looks exactly like what we see when we point our telescopes at the sky. The reason behind such a construction could vary. Perhaps to protect us from knowledge we are not ready for. Perhaps to contain us within a set of beliefs that keep us developing along a specific path. Perhaps as an experiment in isolated development. Think about what this would require from a civilization advanced enough to attempt it. They would not need to physically rebuild the entire universe. They would only need to control what reaches us. Light from distant galaxies travels for billions of years before arriving at our instruments. Sufficient influence over the region surrounding our world could produce any image desired. The light we receive could be carefully arranged. The silence we detect could be manufactured. Every observation we make through our most powerful telescopes could be a maintained illusion, consistent, coherent, and completely controlled. The planetarium hypothesis cannot be falsified any more easily than the simulation argument. Any evidence we gather would be filtered through the same system already filtering everything else. In 1960, mathematician John von Neumann described a theoretical machine with a remarkable capability, a self-replicating probe, a device that upon landing on a new world would gather local materials, construct a copy of itself, and send both copies onward to repeat the process. Each copy would do the same. Within a geologically short time frame, such a machine could spread across an entire galaxy without any ongoing direction from whoever built it. Now apply a darker premise. What if a civilization, possibly one that no longer exists, built self-replicating probes with a mission different from exploration? What if the mission was elimination? The machines would carry one instruction: find any world developing technological civilization and destroy it before it can spread. The reasoning behind building such machines could follow exactly the dark forest logic we explored. A civilization afraid of competition removes every potential rival early. And here is the part that makes this genuinely difficult to dismiss. The civilization that built the machines might have been extinct for hundreds of millions of years before the machines reached our region of space. The machines would keep running long after their makers were gone. Automated extinction, operating on its own, sustained across geological time. This would explain the silence with cold efficiency. Any civilization that became loud enough to be detected would be targeted. Any signal strong enough to be picked up would serve as a homing beacon. The universe would be quiet because anything that made noise was removed. Some researchers point out that we have been broadcasting for over a century. If these machines operate at even a modest fraction of the speed of light, the math becomes uncomfortable. Our signals have had plenty of time to be received by something within range of our stellar neighborhood, and our solar system is vast and largely unexamined. The outer asteroid belt, the distant cloud of icy debris that surrounds us at the edge of interstellar space. We have surveyed a tiny fraction of what exists in our own backyard. Something the size of a car sitting cold and dark among billions of rocks would be completely invisible to our current instruments. Nearly every popular picture of an advanced civilization imagines it expanding outward. More stars colonized, more territory claimed, a galaxy gradually filling with the presence of a growing intelligence. Astronomer John Smart proposed something that flips that image entirely. What if the direction advanced civilizations travel is inward? He called this the transcension hypothesis. The argument begins with a pattern visible in the history of technology on Earth. Over time, our most powerful technologies have not grown larger. They have grown smaller. Early computers filled entire floors of buildings. Then they fit in a room, then on a desk, then in a pocket. Now they are embedded in lenses and watches and chips smaller than a thumbnail. Information processing migrates towards smaller and smaller scales. Smart argues this is not specific to Earth. It is driven by physics. Computation is most efficient at miniaturized scales. The most extreme and interesting physics occurs at the highest densities near black holes at the quantum level, in the territory where space and time themselves become granular. If an advanced civilization follows the physics toward its most efficient frontier, it would not build outward across the galaxy. It would build inward, creating increasingly dense computational environments, disappearing into a dimension of existence operating at scales we cannot yet observe or interact with, eventually inhabiting spaces so small and so energetically intense that they would become effectively invisible to any external observer. This is the silence explained without extinction. Advanced civilizations do not die, they do not hide, they transcend. They move somewhere our instruments cannot follow. Albert Einstein's work in 1905 established something that has never been overturned. Nothing with mass can reach the speed of light. The fastest thing in the physical universe is light itself, traveling at roughly 186,000 miles per second. And even at that speed, the distances involved are almost impossible to make real in the imagination. The nearest star to our own sits about 4 light-years away. A spacecraft traveling at the fastest velocity humanity has ever achieved would need roughly 70,000 years to reach it. A craft traveling at 1% of the speed of light, something far beyond our current capability, would still need 400 years for that same trip. The universe is old enough that advanced life could have developed billions of years ago. But even the most sophisticated civilization ever to exist could not have crossed the full width of the galaxy within any reasonable definition of its own history. The galaxy is simply too wide. The speed limit is simply too strict. Two civilizations could both be transmitting, both be listening, and still never make contact because the physics of space enforces a separation too great to bridge. Now add one more layer that makes this worse. The universe is not static. Space itself is expanding. Distant objects are accelerating away from us. Galaxies beyond a certain distance are moving away faster than light can chase them. The space between us and those galaxies is physically stretching, a process that has no speed limit in the ordinary sense. Here is a possibility scientists take seriously that almost never gets enough attention. We might already be surrounded by alien transmissions. We simply might not know how to recognize them. Think about how our own technology has changed. A person from 150 years ago placed into the present moment would be surrounded by invisible information on all sides. Radio broadcasts, cellular data, wireless internet, satellite signals, all of it passing through the air and through their body constantly. And they would have no idea any of it was there because they would have no instrument to detect it and no framework to interpret what they found. Now scale that problem across millions of years of technological separation. A signal sent by a civilization 100 million years more advanced than we are might be so compressed, so efficiently encoded, so structurally different from what we recognize as a transmission that our best instruments would register it as background noise. We would not call it a message. We would not even call it interesting. We look for very specific things in our search for contact. Narrowband radio waves, because those do not occur naturally and require deliberate technological production. Repeating mathematical patterns. Signals at frequencies associated with the chemistry of hydrogen. These criteria are designed around what we would send if we were trying to reach another civilization right now with our current technology. A civilization millions of years ahead of us may have moved far beyond radio entirely. In 2015, a star about 500 light years away began dimming in patterns that no known natural process fully explains. The light drops irregularly by different amounts in ways suggesting something large and irregular is passing in front of it. Scientists proposed dust clouds, broken up comets, orbiting debris. Some more cautiously raised the possibility of large structures built around the star to harvest its energy. The structured megastructure explanation is considered the least likely by mainstream astronomers. It has also never been completely ruled out. The point is not that we know something artificial caused the dimming. The point is that when we examine things carefully, the universe contains phenomena that our current models do not fully explain. And what we cannot explain, we also cannot communicate with or recognize as communication. The universe is 8 billion years old. Rocky planets capable of supporting biology have existed for roughly the last 10 billion years after enough heavy chemical elements had accumulated from prior generations of stars. Intelligent life, based on what we observe on Earth, appears to require something close to 4 billion years to develop from the first simple organisms. Run those numbers and something strange appears. The universe has been capable of producing intelligent life for roughly 6 billion years. If civilizations arose anywhere near the beginning of that window, they could be 6 billion years ahead of us in development. If they arose near the end, they might not exist yet. We have no way to know where we fall in that distribution concax between civilizations. requires overlap, not just in location but in time. A civilization that rose and fell 3 billion years before our planet formed cannot be called. Their signals, if they ever sent any, passed through our region of space long before Earth existed, sweeping over empty rock. We are not just listening for civilizations in the right location. We are listening for civilizations alive at this specific moment. In a universe this old, most of the intelligent life that ever developed might already be gone. We could be extremely late arrivals in a galaxy that was once full of conversations and is now quiet because most of the participants have finished. Consider what 6 billion years of head start actually means. A civilization that arose 6 billion years before us and survived would have had time to cross the entire observable universe multiple times at realistic travel speeds. They would understand physics in ways that make our current knowledge look like cave drawings. They might have solved aging, energy, even the problem of cosmic timescales. Or they ran into the great filter, or they transcended, or they destroyed themselves in their own technological adolescence billions of years before we were born. There is a version of this problem that some call the temporal paradox. Even if intelligent civilizations are reasonably common across cosmic history, they might almost never overlap in time. Two parties sitting in the same building, separated by billions of years, would never share a room. Their existence would be completely invisible to each other. This version of the silence is not horrifying in the same key as the others. It is lonely in a different way. The loneliness of arriving somewhere after everyone has already left. The loneliness of being separated, not by space, but by an epoch, so long it defies intuition. Carl Sagan described the universe's full timeline compressed into a single year. On that scale, humans appear in the final seconds of December 31st. Everything we have ever called civilization fits into a fraction of a heartbeat at the very end. The universe does not simply allow extinction at certain scales and energies. It produces it across vast regions simultaneously. A gamma-ray burst is the most energetic explosion known to physics. When a massive star collapses, it can release more energy in a span of seconds than our star will release across its entire 10 billion year lifetime. The burst fires a focused beam of high-energy radiation outward at the speed of light. If such an event occurred within a few thousand light-years of Earth and aimed in our direction, the outer layers of our atmosphere could be stripped and irradiated within seconds, leaving the surface exposed to lethal radiation levels for months or years afterward. Scientists believe gamma-ray bursts have likely caused mass extinctions on Earth in the ancient past. The Ordovician extinction, roughly 450 million years ago, which eliminated most marine life that existed at the time, shows signatures consistent with nearby gamma-ray radiation. Scale this up to the galactic perspective. A civilization developing on a planet near the inner regions of the galaxy would face these events far more frequently than we do. Life might arise there repeatedly and be repeatedly erased before it ever reaches complexity. This is one reason some researchers describe a galactic habitable zone, a band of orbital distance from the galactic center, where radiation events are survivable and the chemistry of life is sufficiently rich. Beyond gamma-ray bursts, there are supernovae. When a nearby star reaches the end of its life and explodes, it can irradiate neighboring planets with intense radiation and shock waves that alter atmospheres over centuries. Evidence suggests at least one nearby supernova occurred close enough to Earth to influence conditions on early life. There is also the long-term gravitational instability of stellar neighborhoods. Over millions of years, the gravitational interactions between stars can slowly alter the orbits of planets. A world sitting comfortably inside a habitable zone today might drift outside it over tens of millions of years, losing its liquid water and with it whatever biology had developed during the stable period. Life needs peace. The universe is not especially peaceful. Here is a question that sounds simple. What does a planet need to support complex life? Most people answer oxygen, water, warmth, all correct, all wildly incomplete. The full list, assembled honestly, begins to look less like chemistry and more like a performance that required everything to go right in sequence across billions of years. Start with oxygen. It is the most obvious requirement for life as we know it. But oxygen in the atmosphere of a young planet is not a given. It is a product that life itself must create. On early Earth, the atmosphere contained almost no free oxygen. For roughly 2 billion years, photosynthetic organisms converted carbon dioxide and built oxygen slowly in the atmosphere until levels rose high enough to support more complex biology. That process required extraordinary patience from the planet itself. A stable orbit, a stable star, a climate system that did not swing between frozen and boiling, while the slow, invisible chemistry of atmospheric change was underway. And the oxygen had to land within a very specific range. Too little and complex organisms cannot function. Too much and the entire planet becomes a catastrophic fire risk. The workable window sits between roughly 17 and 30% by volume. Earth maintains about 21%. Carbon forms stable, complex molecular chains that can carry and replicate information in ways no other element matches at biologically relevant temperatures. Nitrogen fills the atmosphere and dilutes the oxygen to breathable concentrations. It also cycles through living organisms and back into soil in ways that sustain biological productivity over geological time. Phosphorus is essential for the molecules every living cell uses to store and transfer energy. It is also one of the rarer elements that biology requires, making its availability one of the critical bottlenecks in biological productivity throughout Earth's history. The window for complex life is defined by intersections. The temperature range where liquid water stays liquid, where carbon chemistry remains stable, where oxygen sits at breathable concentration, where phosphorus and nitrogen cycle effectively. All of these must overlap consistently across billions of years. Maintaining that overlap requires active geology, a moon large enough to stabilize the planetary tilt, a star that does not irradiate the surface into sterility, and an orbital position in the galaxy that avoids periodic bombardment from radiation events. Water is so central to the search for life beyond Earth that scientists working in astrobiology built their entire search strategy around it. Follow the water, they say. Find liquid water and you are in the right neighborhood. Water behaves in ways that are physically unusual. It is one of the only known substances that is less dense as a solid than as a liquid, which is why ice floats on the surface rather than sinking. If ice were denser than liquid water and sank, bodies of water would freeze from the bottom up. Oceans could freeze solid. A layer of floating ice, by contrast, insulates the liquid beneath it. Rivers and lakes remain alive under their frozen surfaces, even in extreme cold. That insulating property is what allowed early life on Earth to survive ice ages that might otherwise have ended everything. Water absorbs large amounts of heat without changing temperature quickly. This makes it an ideal thermal buffer for living systems, preventing the dramatic temperature swings that would otherwise occur inside cells when energy inputs fluctuate. Water is also one of the most powerful solvents in nature, dissolving more substances than almost any other liquid, making it an ideal medium for the chemistry of life. Here is the paradox. Water is one of the most common compounds in the universe. Hydrogen is the most abundant element. Oxygen is produced in enormous quantities by stellar processes. Water molecules are found in interstellar clouds, on comets, on moons of distant planets, in the cold outer reaches of solar systems throughout the galaxy. Water exists everywhere. Liquid water sustained on the surface of a planet, maintained in that state across billions of years, is something else entirely. Almost every world where water exists holds it as ice or as vapor. Water is everywhere in the universe. The kind of water that life actually needs is nearly nowhere. Almost no one thinks of the moon as the reason complex life was able to develop here at all. Our moon is large relative to Earth in a way that is almost unique among the planetary moons we have catalogued. That size has a consequence that runs through all of Earth's history. Earth tilts at an angle of roughly 23 degrees relative to the flat plane of its orbit around the central star. That tilt is what produces seasons, the gradual shift between warmer and cooler periods as each hemisphere faces the source of energy more directly at different times of year. Without an outside stabilizing force, Earth's axial tilt would not stay near 23 degrees. Gravitational interactions with the other bodies in the solar system would cause the tilt to wander chaotically across millions of years, cycling through climate regimes so extreme that stable ecosystems would be nearly impossible to sustain. The moon prevents this. Its gravitational pull acts as a gyroscopic anchor, holding the axial tilt within a narrow and relatively stable range across hundreds of millions of years. The result is seasons consistent enough that life could evolve within predictable patterns. Remove the moon and Earth's tilt wanders. Climate swings to extremes no existing ecosystem could survive intact. The evolutionary pressure that builds complexity, that drives nervous systems, that eventually produces cognition, might never have arrived in a stable enough environment to take hold. The moon itself formed through what most scientists describe as a collision event. A body roughly the size of Mars struck the early Earth at an angle that vaporized significant portions of both objects. The debris gathered in orbit and coalesced into what we see tonight in the sky. Slightly different parameters for that impact, and the moon does not form, or it forms smaller with insufficient mass to stabilize the tilt. Stellar wind is a continuous stream of charged particles flowing outward from a star at speeds ranging from 200 to 900 miles per second. It fills the inner regions of every solar system and scours every surface it reaches. Mars is the most vivid case study of what stellar wind can accomplish when left unopposed. Scientists believe Mars once had a thicker atmosphere, a warmer climate, and possibly liquid water pooling on its surface in the distant past. Then, roughly 4 billion years ago, the planet's internal magnetic field weakened and eventually died. Without a magnetic shield, the stellar wind began stripping away the Martian atmosphere at a rate of hundreds of grams per second. Over geological time, Most of that atmosphere was lost to space. The surface became cold, dry, and hostile to any biology that might have existed. Earth is protected from the same fate by its magnetosphere, a region of magnetic influence generated by the circulation of molten iron deep inside the planet's outer core. The magnetosphere deflects the incoming stream of charged particles, bending it around the planet rather than allowing it to erode the atmosphere or bombard the surface directly. We occasionally see the edges of this shield at the poles, where particles that make it through the deflection spiral down along magnetic field lines and collide with the atmosphere to produce the northern and southern lights. It is one of the only moments when the invisible shield makes itself visible. Generating a sustained magnetosphere requires a specific internal architecture. A large enough iron core, enough internal heat to keep that core molten and circulating, enough time without cooling and solidifying. Earth has maintained its magnetic field for billions of years. Mars lost its field billions of years ago and has been steadily losing its atmosphere ever since. Suppose you were asked to build a world capable of producing intelligent life. You have unlimited resources and unlimited time. What would the checklist look like? Begin with the galaxy type. Elliptical galaxies produce too many violent events. Irregular galaxies often lack sufficient heavy elements. You need a large spiral galaxy with active star formation, rich in the elements forged by previous generations of stellar explosions. Within that galaxy, you need the right orbital position. Too close to the galactic center and radiation events will repeatedly sterilize any developing world. Too far from the center and the chemical building blocks of complex biology are too sparse. Within the solar system, you need a star of the right type. It must burn consistently enough to allow biology to develop across billions of years without periodic flares that strip atmospheres or cook surface life. You need at least one large planet in the outer region of the system to sweep up debris. You need the habitable world placed at exactly the right orbital distance for water to stay liquid, and that distance must remain stable across geological time. The habitable world itself must be the right size, large enough to hold a thick atmosphere and sustain internal heat, small enough that gravity does not prevent biological movement. You need active plate tectonics. You need a large moon formed by a specific kind of impact event. You need an active magnetic field generated by a molten iron core and sustained without interruption across geological timescales. You need the right chemical delivery, and you need the first chemistry of life to arise from all that material. That first step from raw molecules to something capable of self-replication remains one of the most poorly understood transitions in science. Every single one of those requirements must be satisfied in order without interruption across billions of years. When researchers attempt to calculate the probability of all of that happening again, the answer changes how you think about what it means to be here. In 1960, astronomer Frank Drake pointed a radio telescope at two nearby stars and listened. He heard nothing meaningful, but the act launched one of the most sustained scientific searches in history. The search for extraterrestrial intelligence became a formal discipline with dedicated researchers, purpose-built instruments, and institutional funding. For decades, the expectation was straightforward. We listened long enough and carefully enough, and eventually the silence breaks. That expectation is aging badly. Over 60 years of listening, the search has detected exactly 0 confirmed alien signals. One candidate, recorded in August of 1977 by a researcher named Jerry Eman at a facility in Ohio, was so unusual and so structured that Eman circled it in the printout and wrote a single word in the margin. What he wrote was, "Wow, the signal has never been detected again." Despite thousands of subsequent hours spent scanning the same region of sky, it remains the most compelling candidate ever recorded, and it appeared once and vanished without explanation. Some researchers have responded by expanding the search. Broader frequencies, larger portions of the sky, more sensitive instruments, more computing power devoted to analyzing the data. But a quieter and more unsettling conversation has been developing in parallel. Some researchers are beginning to question whether the fundamental assumption driving the search, that an alien civilization would transmit signals detectable by our current technology, is valid at all. A civilization millions of years more advanced than ours may have moved entirely beyond radio waves. Their communications may be so compressed, so directional, so embedded in a medium we have not yet discovered that our instruments would register their signals as meaningless background noise. We might be sitting at the edge of a vast conversation that our equipment simply cannot resolve. There is also the question of intent. Why would an advanced civilization broadcast to the general galaxy? On Earth, our own signals are already becoming harder to detect from interstellar distances. We are moving toward more directional, encrypted, and efficient communications. In a few decades, Earth's radio signature will likely be substantially weaker than it is today. If we are already evolving toward less detectable broadcasting, other civilizations may have completed that transition billions of years ago. The next century on Earth is unlike any previous century. The difference is convergence. Several technologies, each individually capable of reshaping civilization, are maturing at the same time and interacting in ways that no one can fully model in advance. Artificial intelligence is developing faster than the researchers building it anticipated. Biotechnology has developed the ability to design and synthesize biological organisms from scratch. What began as an effort to cure disease has become the ability to engineer entirely new forms of life and to produce biological agents with characteristics not found in nature. Nuclear weapons have not disappeared. Climate systems are changing in ways that are producing real and measurable disruption to agriculture, infrastructure, and population distribution. Any single one of these pressures would define an era. Facing all of them simultaneously at accelerating pace may exceed the adaptive capacity of institutions and governance structures designed for a very different world. Here is what this reveals about the Great Filter. If civilizations regularly pass through a period where their destructive capability accelerates beyond their wisdom, and if most of them fail to survive that period, then the silence of the universe is exactly the output we would expect to observe looking outward. Empty galaxies would be the natural result of a cosmos where intelligence repeatedly develops the power to destroy itself, and often enough does. That recognition carries something unusual inside it. We are not the first to arrive at this convergence. We may simply be the first to understand what it is before it resolves. Every civilization that faced this moment did so either without knowing what it was or without being able to do anything about it. We know what it is. Whether that knowledge changes what happens next remains genuinely open. Imagine Earth goes silent tomorrow. Whatever the cause, the civilization that covered this planet in cities, satellites and signals simply stops. Every transmitter goes dark. Every instrument goes cold. What would remain? The signals already sent are still traveling. Radio waves from the earliest human broadcasts have been expanding outward for over a century, spreading in every direction as a growing sphere of electromagnetic radiation. The oldest signals are the faintest, diluted by distance to levels that would be extremely difficult to detect, even with sensitive instruments. But they are out there, moving at the speed of light, washing over thousands of star systems as they expand outward through the galaxy. 2 probes launched in the 1970s carry engraved metal plaques depicting a man and a woman, a diagram of our location relative to a set of pulsars used as navigational references, and a simple image of our planetary system. These probes are now beyond the boundaries of our solar system, moving at roughly 27,000 miles per hour, making them the most distant human-made objects in existence. At that speed, they would reach the nearest star in about 70,000 years. 2 other probes from the same era carry golden records, metal discs encoded with sounds and images from Earth, music from dozens of cultures, greetings spoken in multiple languages, the sounds of rain, wind, ocean surf, and human laughter. Photographs of anatomy, landscapes, and cells. They are the most carefully considered physical artifacts humanity has ever placed in the cosmos. If everything on Earth ended tonight, these objects would continue. The probes would keep moving through deep space for billions of years. The light from our broadcasts would keep expanding outward. The reflected light from our cities, captured in the right wavelength by a sufficiently powerful telescope aimed at our star during the current era, would show a brief, anomalous brightening on the 3rd planet, followed by darkness. Any civilization capable of detecting and analyzing that signature would know something was here. They would know it developed technology. They would know it produced structured electromagnetic emissions. They would not know why it stopped, and they would face the same question we face when we look at the silence around us. What happened? Was it the filter? Was it transformation into something undetectable? Was it simply time? The silence we would leave behind would be identical to the silence we are trying to explain. Every civilization that has ever existed, if any, encountered the universe the same way we do, looking outward, listening, receiving nothing back, wondering why. Every one of them left something behind, even if only light and unanswered questions. We are doing the same thing right now, unknowingly building a record of our existence that will travel long after we are gone toward listeners who may find it in a future too distant to imagine. We followed the silence to the edge of what science can currently answer. We crossed the Fermi paradox and the great filter. We considered machines left running by civilizations long dead, false skies built by something advanced beyond understanding, and the physics of a universe that enforces isolation through its own geometry. Every thread led to the same place, a question that has been waiting inside each chapter, gathering weight. Are we the last? Are we the first? Or are we simply alone? These 3 possibilities are not similar. They carry different implications, different weights, and different obligations. If we are the last, then something ended everything before us. The universe had other civilizations, possibly many, and they are gone. The great filter was real, it was effective, and we are the accidental survivors of a cosmos that consumed everything else. Our survival so far is not evidence of safety. It is a narrow statistical exception, and the filter may still lie ahead if we are the first something else is true. Life is so rare or intelligent, so improbable, that despite billions of years of cosmic history, nothing before us ever developed the capacity to look outward and ask this question. We are not survivors. We are a beginning. And that means the future of awareness in this entire region of the universe, whatever that future holds, runs entirely through us. If we end ourselves, we may not just end a civilization. We may end the only experiment in conscious reflection this part of the cosmos will ever produce. If we are simply alone, the rare Earth picture is correct. The universe, despite its scale and age, has managed to produce complex questioning life in one place so far. Others may exist, separated by distances and timescales that make contact effectively impossible, regardless of technology or intent. Each of these answers is terrifying in a different register. The last says we are in danger. The first says we carry something almost impossibly fragile. The third says the loneliness we feel looking at the empty sky is not a feeling, but a fact. But here is what none of those answers changes. We are here right now, thinking, building, sending signals outward and instruments farther still. Something in this universe, in this specific location, at this specific moment in cosmic history, became aware of itself and looked up. The universe did not make room for that. It did not arrange the galaxy for our benefit. It did not schedule our arrival. We came anyway, out of chemistry and time, and an improbable series of events that would have ended at dozens of different points and did not. The silence is real. The emptiness is real. The filters, the risks, the physics, the vast indifferent scale of it all are real. And yet we are the thing this universe grew that learned to wonder about all of it. Whatever the silence means, whether it is a warning, an accident, a manufactured illusion, or simply the natural output of a cosmos where life like ours is extraordinarily rare, we are the only known thing that ever looked at it and asked why. That is either the loneliest sentence ever spoken or the most extraordinary one. It might be both.